Yeah, I'm more than happy to having Guy Andreboy again on one of our webinars today. As many of you know and maybe listened to webinars before, Guy is a cognitive scientist and an engineer, and he was working a long time as chief scientist for human-centered design at the NASA Space Center in Florida. We met Guy some years ago, and we are very happy to work together with him because he is the one who brings science back to practice and learn from practice back to science. And it helped us a lot in designing some of our systems. And the more we get that into aviation and especially air traffic control, the better it will be. The webinar today is scenario-based design. It's one of a vital part of human-centered interactions or human system integration. And Guy will show us the product method based on examples from aviation, but also from telerobotics. And as Dana already said, any questions, please put it in the question and answer section, and we will talk and discuss that on the end of the webinar. Thank you, everyone. Guy, the floor is yours.
Thank you very much, Jörg and Tony and everybody you're control to me today. So I share my screen. Can you see my screen?
Yes, we can, Guy. Thank you.
Okay, great. Okay, so today I'm going to talk about scenario-based design, and more specifically about the method that we have and we are still developing, called procedural and declarative knowledge. Check why. Okay. So the basic idea is the following. Scenario-based design is a family of techniques in which the use of a future system is concretely described at an early point in the development process. So in fact, in doing this, I mean, try to describe people using technology. You know, it's interesting. I will come back on this, but for quite a while now, we want to predict what a system could do, but prediction is not anticipation. Anticipation is about imagining possible futures, future scenarios, future technology, future organization, future jobs, and try to run simulation in order to validate that. This is very different from prediction, or at least causal prediction. So this is what scenario-based design is about. And the idea is to do that as early as possible during the design process. So I'm going to take two examples. Just for as a reminder, I'm a professor at Centrale Supélec in Estia in France, Paris, and I'm leading a chair called FlexTech. And within FlexTech, we have several projects. At the moment we have 5 projects running, from air combat to these two here. Virtual air traffic control is not virtual air traffic control in the civil aviation, but in the military aviation there. And I'm going to talk about Mohican. It's a project that we had with the French Ministry of Defense. And so scenario-based design is about storytelling of the current practice first. I mean, we need to figure out what is going on today. And we do that with experts. And experts are very good at telling stories about what happens. And then we have to collect these stories and make some more concrete stuff. we want to reveal the aspects of the stakeholders and their activities that have implications for design. Then once we have a common ground for the project team, then we try to describe activities of what we call the problem domain in order to anticipate some future scenarios. But one thing that is very important is to ground what we do in human-centered design and now in human systems integration on current activities and try to depart from that and see what we could do in the future. Scenarios are stories. So I'm sure some of you know about this diagram I'm going to comment now. You know, for a long time, we are using operating procedures that automate people in life-critical systems. We automate, in fact, human functions. And when we put these procedures in the machine, then we automate the machine, and then we automate machine functions. But all this is, all this is in a very rigid world, in a known world. And when, you know, for expected situations, but what happens for unexpected situations, something that is rare, sometimes unknown. What do? You continue to apply procedures. If you do that, most of the time, it could be extremely dangerous. So you solve problems. And sometimes solving the problems, you go back to an unexpected situation. But the first thing to do is to solve the problem. And for that, you need autonomous agents. And then once you have these autonomous agents, you need to coordinate these agents. And here, you need to be in a flexible environment. You need to have flexibility to solve problems and competence as well. I mean, this is where autonomy is entering into the picture. So in fact, all this leads to what we call human and machine function allocation. So we need to define functions for the procedures, for the automation, and for problem solving. We call this shift today from rigid automation to flexible autonomy. It's very fashionable to talk about autonomy today. And I'm going to enter into these details in a few minutes. So all this is done in my FlexTech chair. The shift is also from single agent approaches to multi-agent approaches. So this is the remote virtual tower that I was talking about. This is in the south of France. It's in Mont-de-Marsan at the French Air Force base there. And we started with stories from you know, the people controlling the traffic. Not in this, we built that later, but in the current activities. And then we tried to find out what would be the objective to build this machine here, or this environment. We want to save costs, and also we want to save cost on maintenance, on the operation and maintenance. We want to be able to have a very flexible system where we can put the tower almost anywhere we want. I mean, sometimes it's very difficult on the battlefield, and then we want to deploy that for military external operations, and especially in isolated areas. And the game there is to set up the sensor where it's the most appropriate and the most useful. And then we want to work on system performance, provide controllers with the tools that were not available in traditional towers as well. So in fact, not only we want to be flexible, but we want also to provide some additional capabilities that were not there before with a fixed tower. So in fact, we would like to provide the same features as a traditional tower, and in addition, provide some additional capabilities that will enhance the control and the management of the traffic. So, in fact, the idea there is to talk with the stakeholders and to develop stories. So designing an air traffic control virtual center as a complex socio-technical system, we would like to follow this human system integration approach that I'm going to present today. By the way, I would like to acknowledge my PhD student, Alexandre Didier, who is actually developing this for almost 2 years now. So in fact, the idea is this. And here, these are definitions that are very important, as is and to be. So we develop as is scenarios and also to be scenarios. And we want to compare these scenarios. Of course, in order to compare these scenarios, we need to develop metrics to be able to judge what is good, what is not good, etc. So for this, we are using a language called BPMN, Business Process Modeling and Notation, that is based actually on another approach that I will develop later. That's called I-blocks, interaction blocks. And then we develop scenarios as is and to be. So that looks like this. This is a very simple one. In fact, we have walls of these scenarios when we develop, you know, the case that I'm talking about. So, in fact, what is PRODEC, the method, the scenario-based design method I want to develop now? First, we need to know about procedural knowledge. What is procedural knowledge? Procedural knowledge is coming from cognitive psychology, and that was used by computer scientists to develop procedural languages, you know, like Fortran or as opposed to declarative knowledge or declarative languages like you know, the Prolog or things like this. So procedural knowledge enables you to develop task scenarios. And here I need to make a distinction. Sorry, there are lots of definitions in order to define this. But the task is what you need to do, what you want to do, what is prescribed. And the activity is what you effectively do. So in fact, in the first place, you are only capable of developing task scenarios. And then when you can see the people acting in the field, on the field, then you can develop activity scenarios. So you translate what you see, what you observe into activity scenarios. And then the trick is to compare the two, of course, in order to find out the discrepancies between task scenarios and activity scenarios. Then you try to form context. Then another definition, a context is a set of situations that are persistent. You know, when I say I'm in the context of takeoff, persists for you know, from the one end of the runway to the takeoff, the real takeoff, rolling on the runway. And then you have, it's not instantaneous, it takes a while. And its context is at the same time described in time, but also in space. And it's the persistence define the context. So you have the phase of flight that is called takeoff, that is a context. And then you have the initial climb, and then you have the cruise, and then you have the approach and descent and landing. So these are contexts, if you like. Then also the procedural knowledge is about operational experience. Then you need to have people, experts, experienced people, to help you develop these scenarios. procedural knowledge. And the formalism that we are using is called interaction blocks, I blocks. I will come back on this later. On the declarative side, you know, it's like, for instance, if you describe a play, a theater play, you know, the procedural knowledge is the scripts, are the scripts for the comedians, for the actors. And the declarative are the actors themselves and the objects on the scene, you know, the objects and the agent configuration. It's about configuration of the system that you observe or you develop. Then here, we want to talk about system of systems. So in fact, a system is described by various kinds of things, but it's always include other systems. Of course, there is a level of granularity that you need to stop, where you know, but a system includes systems, and a system belongs to a bigger system. So in fact, this is the difficulty in the representation, but a system of system is a very important concept. And this is interesting because we have to match the system of system definition to the context of context. This is orthogonal, and I will come back on that in a few minutes. Then you have here another kinds of expertise, the engineering design expertise. Of course, everybody is not good in everything. I mean, you have jobs, you know, that you have learned things to do. And here, this expertise is about designing systems, okay? And then the formalism there is made in the, I mean, as follows: a system is considered as a function and structure. A system is defined by the structure and has some functions, you know, and then we talk about structures of structures, of course, and functions of functions. So in fact, the idea is instead of the classic approach of engineering that starts with the declarative knowledge and then put that at work when everything is developed in the flight test, for instance, and test the procedural knowledge, we want to start procedural knowledge from the beginning in models and simulation and build incrementally declarative knowledge and restate the procedural knowledge in various, I mean, probably in a few iterations. So as I said before, there are two kinds of architectures: the context architecture and the system architecture. You know, if there are system engineers in the, you know, in the audience, you know what the system architecture is about. The context architecture is about procedural scenarios, as the system architecture is about declarative configurations. And then the declarative scenarios are coming from operations people. And here it's coming from engineering design people here. And then we want to iterate on these kind of things. All this seems to be very obvious when you look at it, but it's not. Because for a long, long time, we didn't develop this part very well. We developed that, and we left this for operations sometime very, very late. So we want to include this from the very beginning of the design process. This is why the concept of human-in-the-loop simulation is extremely important, and I will come back on that. So in order to do that, and I'm sure that if you followed some of my lectures before, you have seen this. Anytime you want to develop an artifact is a system, if you like. Artifact, the meaning of artifact is something that is designed by people and built by people. Is to execute a task. So if you want to go faster to a place, then you build a car, you know, and then the user is the person that actually execute the task using the artifact. So what you do first is you do a task analysis. This is the first scenario that you can develop. And then doing that, you figure out what we call the information requirements for the artifact. What do you need to develop here in order to execute the task faster, better, more accurately, more whatever, the metrics you're going to use. But the problem is here you have something else, that whenever you develop an artifact, then you have technological limitations. You cannot do everything you want. So either you invest more money and then you can develop a new system, or you try to adapt to create a new system using older systems by assembling them, so integrating them. And then here on this side here, you have what we call the adaptation of the artifact to the user. It's called ergonomics. And then the adaptation of the user to the artifact is called training. And this is where you develop procedures. Once you start a first cycle here, then you can run a human-in-the-loop simulation. And then you can observe the activity. Remember, I defined the task is what you want to do. The activity is what you really do, what your user really do. Then you can run an activity analysis and compare the two. By comparing these two things, then you improve the rest. In fact, this is the way you do it. Then let's put something else, the organization. You never develop something in the vacuum, or you're going to have surprises after that. As a matter of fact, I like surprises, but surprises during the design, not during operations. So in fact, as early as possible, you have to introduce this concept of organization. And then here, by on this side here, the link between user and organization, we call that social issues. Sometimes, I've been involved in this when we shifted from 3 crewmen cockpits to 2 crewmen cockpits. Believe me, we had social issues by removing somebody there, especially in France. But it's not only social issues. You have this adaptation of things that the role of people in the organization, in the society, if you like. And then you have this line here, task organization. This is about analysis of jobs, job analysis and role. What will be the role of people when you design this new artifact? So in fact, you're going to modify the organization, you're going to modify the task here. And then here you have another line that is artifact organization, where you try to better understand, the evolution that causes this artifact in the organization. And the other way around, sometimes, there are some habits that are coming from the organization. Today, with the smartphones, we have lots of habits that we didn't have only 20 years ago, and that you have to take into account in the artifact. And then if I add another point here, the situation. Situation means, if you design an aircraft or an air traffic control center, the situation could be the weather, the external events that actually will influence the task and the use of the artifact, and also the organization and the people. So here on this side, user situation, you have what we usually call situation awareness. Using the artifact, executing the task, am I aware of what is going on? Here you have the situated actions. So in fact, the task is not context independent. It's really context dependent. It's situated. So there is a very good description of this that was done a long time ago on situated action during the 80s. That was done at Xerox PARC. I don't remember, but this is we know that very well. So here on this link here between situation and artifact. You have everything that is related to usability and usefulness. Is the artifact usable in any situation or in a limited set of situations? Is it useful, etc.? And then on this one, you have all the the way the organization is set with the supervision, cooperation, coordination, mediation, all these kind of things. So in fact, doing scenario-based design is also doing this. It's not only describing the events one after the other, it's also starting to develop what I call the autos pyramid of these scenarios. And you could tell me, well, but where is the human here? You know, for 45 years, I've been working in human-centered design and now human systems integration, and say, well, but you're using models for humans. Yes, I participate in the development of this one, MIDAS at NASA Ames Research Center in California. I think that was developed for 20 years with lots of people. Unfortunately, in the end, it was so complex. I mean, this model, MIDAS, was a model of pilot and was able to land an aircraft very, very successfully. But in fact, in order to understand what was going on, you need other models to understand it. So in fact, it's a kind of recursive approach of modeling. I developed myself during the certification of the 2 crewman cockpits with Airbus, the message model as well. If you're interested, I have papers on this. Later on, people develop personas, the persona approach, where you try to have a generic model of a human with specific characteristics and things like this. But as far as I'm concerned today, the best model is the real one. I mean, the human. And in fact, human in the loop simulation is the best for me at the moment. This is very personal approach, but this is what we are developing right now in my chair, FlexTech. The cost of this is that you need to have very good model and simulations of the artifact or the system you are developing, and put the people in the loop and use that as a video game or computer game, whatever you want to call it. But this is very important because in a few minutes, you're going to realize if the system is good or not. So in fact, the only human models that are useful at the moment for us are the Rasmussen's SRK skill rule knowledge model, Hensley's situation awareness model, and other of that kind. It's I cited 2 here that are very well known, but these are more qualitative models than quantitative models. So, as I said, PRODEC is a scenario-based design approach. And I already introduced the distinction between task, what is prescribed, and the activity, what is really performed, executed, effective, in fact. So when you start and you want to develop a new system, a new air traffic control system, for example, the first thing to do is you're going to start with the task. You cannot do with the activity. I mean, you can observe the people doing the control, of course. I mean, that's but what exists today, not what will exist in the future. So in fact, you can do a task analysis. You imagine, you anticipate some tasks. And then for doing this, the first thing to do is to do brainstorming. And we have developed methods for that. We have developed the GEM approach, a group elicitation method. I will maybe have time to describe that in a few minutes. In order to put on the paper concrete ideas about new functionalities, new way of thinking about user needs and how to meet them. So you start from the real world, and then you talk with the experts. I mean, air traffic controllers in this case, and then you get that. A claim analysis, task analysis and trying to identify trade-offs as you move forward with prototypes. So in fact, that's the second part. Third part, activity observation, human-in-the-loop simulation, observation protocols, analysis, and experience feedback because it's never finished. Even when you have developed the system, you have to improve the system as you go. So in fact, the experience feedback mechanisms are extremely important. But be careful with this one, because in the nuclear industry, and I had 2 PhD students on this and worked with the nuclear industry for a while. And in fact, these guys were extremely proficient on this. They had experience feedback mechanism extremely well done, except that these experience feedback mechanisms were cumulative. So in fact, after a while, then you accumulate recommendations and procedures. And it takes a while actually for the people after that to execute the procedure that are mandatory to execute. So instead of having a cumulative there, you need to have an integrative approach. So you need to integrate the feedback, the experience feedback that you get into the knowledge that you have coming from previous experience feedback. And that's another story that I will not comment today. That could be another seminar. So as I said before, we are not talking about predictions, but anticipation. We describe these as-is scenarios and to-be scenarios. And here, the difficulty is to associate 2 things that are antagonist. The experience that is conservative, people who are very experienced, they know how to do things, so they most of the time don't want to change. And then creativity is out of the box knowledge, where you anticipate something that you think that is very good to do, but you have to combine experience and creativity. This is where the trick is and the difficulty. So for a long time, all this was not very well done. Why? HFE means human factors and ergonomics. Human factors and ergonomics started after the Second World War and developed. And in fact, was mainly based on the observation of activity before the design of a system and when everything was built. And we call that most of the time corrective ergonomics. 95% of the human factors and ergonomics today is still done that way. Starting in the mid-80s, HCI, human-computer interaction, started because the microcomputers invaded our world. And then there, it's interesting because in computing, in the computer medium, task and activity are very similar. So in fact, the people developed task analysis methods, and they included that in the design of user interface. In this case, I mean the computing user interfaces, the desktop and things and others. And what was designed there is interaction design. We designed the interaction, human-computer interaction design. The problem is this part, and I've been involved a lot in this part myself, was not at all very integrated in large complex systems like air traffic control or nuclear power plant development or air combat systems, where you have a lot of things to consider with the physics and not only cognition, but also physical stuff and a large number of things to be considered. And then in the mid-2000, 2005 or something, I mean, after the 2000, human systems integration started. It started within an organization called INCOSI, International Council on Systems Integration. And there, why that could be done is because the computing was so developed that we could do human-in-the-loop simulation very easily compared to the past. You know, I want to cite the Falcon 7X done by Dassault Aviation, was done as a computer game, huge stuff, and flown by test pilots longer before it was built. So in fact, we could test human factors, we could test the activity at design time. That was the big revolution. And it's still big revolution. So in fact, here you can do scenario-based design using human-in-the-loop simulation. It will cost a little bit more in the beginning, but in the end, you will actually have a lot of benefit because you will not put patches like we do most of the time. Then let me enter into more fundamental stuff. And a system could be used to represent a procedural entity. So in fact, a system transforms a task into an activity. You remember, prescribed task, effective activity. And that defines the context space, in fact. And then orthogonally, you have the system representing a declarative entity. A system is characterized by a structure and a function that themselves are defined by a role. You know, you define, for instance, the role of a carrier delivery man, for instance, a postman. The role is to deliver letters, you know. By the way, a system could be a human or a machine. You know, it's interesting because the term system is used here as a representation. When a medical doctor says, talks about the cardiovascular system, it's not a machine, it's an organ, it's a biological thing. So in fact, when we use system, it's both for human and machines. So role, the postman delivering letters, context, time context, space context, time context from 8 to noon, from 2 to 5 every day, 5 days a week. The space context, I mean the neighborhood where the delivery is done. And then resources that are systems themselves. So in fact, this is interesting because here you start to see, I was talking about system of systems, but here you see that the definition of a system is because a system includes other systems. The postman, for instance, has other systems that are external, like the bicycle, the bag, but also internal, cognitive, also the pattern matching. This person needs to pattern match the name of the street with the name of the street written on the letter and the number on the door, etc. So in fact, a system is described by structure and function with these kind of things, and that could be physical or cognitive and human or machines. That defines the system space. You know, this seems to be a very simple definition. It's extremely complex. So in fact, we are developing right now a support for a product that will enable, you know, to develop these declarative entities incrementally on a computer, in fact. So all this needs to be thought in 3 ways. And I call that the top model: technology, organization, and people. On the technology side, you deal with automation most of the time. You know, you have a system, and then you try to put some more cognition in the system and some additional structures that will enable the technology to be improved. On the people side, you develop skills and knowledge. People learn a new job when you design a new system, starting from the old job, for instance, but or a radically new job. Organization, you deal with regulations. And no matter what, you will have to develop these regulations. If we go into more detail, then here at the moment, AI and data science are leading, but it's not the only things. on the people side, you have procedure following and problem solving. You remember this schema with rigid and flexible? This is extremely important here. And then here on the organization side, coordination is always something that you need to consider. So in practice, you have a target audience, okay? In our remote virtual tower for the military, the audience is, you know, the air combat, and the people have to land somewhere, or you know, and need to organize this, and the target audience is the people dealing with these kind of things. And intent, more flexibility for this kind of thing. Subject matter experts, these are the people on the field, in the field that will provide their expertise in testing the prototype, for instance. Then they also provide storytelling for the task analysis. And then we build the prototype. And then these operation people interact with the prototype. You observe the activity and you do an activity analysis. Then you do a function analysis with the declarative approach that I already mentioned. And then you modify you know, the task analysis and the prototype, and you iterate on this as many times as you can. Probably it's a matter of resources and funding, but in fact, you need to anticipate these iterations. So to remind you some things I've said in one of my webinars last year, in fact, you know, when you deal with life cycle human systems integration, life cycle meaning you go from design to manufacturing, to certification, to operational support and dismantling. Then with the technology center approach, most of the time people commit too early on the resources. This is mostly because, you know, the organizations are linked with the suppliers, and the suppliers have on-the-shelf stuff, and they may actually build something new, but they have, and then you commit sometime too early. And then, of course, the design flexibility drops, and you learn about the system as you use it, as you manipulate it one way or another. In fact, here it grows very fast here because you're using it. This is the flight test, for instance, for an aircraft. Now, if you take a human-centered approach with human-in-the-loop simulation and scenario-based design approach, then it's interesting to see that you learn much earlier on the system knowledge. With an important issue to consider, that is actually tangibility. Is it tangible to test this on in a virtual world only? That's a big question. But in fact, you learn more by you know, testing the human-in-the-loop simulation on a digital model that are more and more accurate, more and more close to the real world. Then you know, and then you can re-inject that in the system very early. The design flexibility is following a curve that is the concavity is actually opposite to this one. In fact, you can stay flexible longer time because you can do that in software and not in hardware. And then the resource commitment are also following the same kind of idea. The concavity of the curve is inverted here. So in fact, it's interesting to see that this modeling and simulation, this part, we are working right now with a large company making helicopter engines, and they are maintaining 80% of their engines that are sold in various places in the world. And then we have a digital twin approach that is actually a modeling and simulation of these engines that we can test. So in fact, what we did here, you know, we expanded this on the whole life cycle, in fact. And the digital twin here that is a representation and a model and a simulation of the real stuff. Here is an engine, but it could be a power plant. It could be, we have done that with Total Energy as well on a power plant. So you run scenarios in order to better understand the problems, in this case, for the engines. If we expand the human-in-the-loop simulation to the digital twin, in fact, you can test the what if, and this is what you do with the anticipation. What would happen if I do that? That also constitutes a vivid documentation. And this is interesting because now we can see that in systems engineering, we talk now more and more about model-based systems engineering, MBSE. And then the digital twin is really a model of the thing. And in fact, where you need to be able to integrate experience feedback. I was talking about experience feedback as a problem when you accumulate, but here you have to integrate incrementally in the model, the experience that you get, and in fact, improve the model. Okay? This is a kind of organizational memory about the thing. And then the digital twin here could be used as a virtual assistant, as a user interface, if you like. This is interesting because there are studies now that we call human-machine teaming. I've been working on this with the French Air Force, and in fact, the digital twin could be used as an augmented, if you like, system for the human, and that collaborate, with the human. So this is about multi-agent collaboration. So in fact, we are developing this kind of things as well. Okay, so it's if I summarize this, during the 20th century, we were going from means to purpose, doing an aircraft, for instance, and then realizing that there are people in the aircraft to run it. We develop cabins, cockpits, and in fact, if I put that in a more abstract form, then you have a physical environment, then a control and management space, and a human in the loop, humans in the loop here. So during the 20th century, we had this approach that I call inside out, with many disciplines like engineering, ergonomics, human-computer interaction, and automation. So means to purpose, 21st century, we can do from purpose to means. This is where scenario-based design enters into play. So in fact, instead of waiting long to test the system, the flight test, then we can start from the early stage of the design. And we call that, the approach is called outside in. So in fact, we start from the scenario as is scenario, and then we build the to-be scenarios, and then we build this declarative environment, and then we test it, and then we tangibilize incrementally the system that is being developed. So in fact, incrementally, we separate the fully virtual environments into a physical environment, and then to finish, of course, with the real environment in the end. So this is what human systems integration enters. So I already described this diagram here, you remember, rigid and flexible. But I want to emphasize this point. Complicated is different from complex. Complicated, when something is complicated, most of the time is because it's not very well done. Then you try to make it simpler. And we have done that. I worked with Airbus on the management of procedures, operations procedures, the FCOM, Flight Cooperation Manual, for a long time. And we're trying to simplify, to simplify, not simplify the content, but simplify the use of it. And in order to present the most appropriate stuff to the pilots, then you try to be more rational and to try to be useful. This is really that. And then today we are moving towards this flexibility where complexity enters into play. And complexity is very, you cannot simplify something that is complex. You can become familiar with it. And that's a big difference. You know, a human body, you cannot simplify the human body. It's the way it is. You have hands, you have a heart, you have legs, and you have a brain, and then all this is interconnected with lots of interconnections. And then you have to get familiar. Becoming a medical doctor takes 8 years, and then you specialize and you do 12 years to studies. So in fact, you become familiar with a complex system. And then you have to work on the understandability of that and the usability of it. Then, as I put it here, complexity involves maturity. You understand a system when it becomes more mature, in fact. You understand, and when you understand it good, so at the beginning of the 20th century, for instance, you know, the drivers were coached. In fact, they were not coaching horses, but they were driving a car. But the owner was in the back, and they were also mechanic. I mean, the maturity of the technology was not the way it is today for the cars, and the maturity of the use of the car was not what it is today. At the end of the 20th century, most of the people didn't know what a carburetor was. So just, you know, it's not, but you have to understand that at some point you have to stop because you're going to break the car. And then there are several levels of readiness that we know about for the last 20, 25 years now. And the first organization that developed the technology readiness level, the TRLs, was NASA. You have a TRL from 1 to 9. And then we know pretty well what we mean by technology readiness level. But in fact, these are not the only one that you need to consider. You know, you need to consider other levels. And the second one is human readiness levels. At the moment, the best list of readiness levels is done by the US Air Force. We have discussed that last year in November in California. And this is of course, I mean, all this is improving, is probably, I don't want to make a meta remark here, but we have to mature these maturity levels. So, and then the third one is the organization readiness levels. So, because you know, an organization is not necessarily mature enough to use the technology that is at technology 9, you know, TRL 9. It's not the same. So in fact, we need to develop that, and you need scenarios for that. And then you can develop scenarios for TRL, HRL, or ORL. So flexibility, you understood why flexibility, I mean, the kind of thing that we deal with when we talk about flexibility, from complicated to complex, rigid to flexible, from operations and engineering on both sides. So we need a systemic representation that covers that both humans and machines. I have a question. How am I regarding time?
Heidi, you can still have about 5-10 minutes max. Okay.
So I already presented that in the previous webinar. A system, as I said before, could represent a natural system, a human, or an artificial system, a machine, or can be a natural system representing a natural entity, or be an artificial system representing an artificial entity, characterized by a function and a system and a structure that could be physical or cognitive. So all this has been done. So for a long time, a system was considered as isolated, but today we need to consider that the system is connected to other systems, and the system is a system of systems and is included in another system. So the problem now, as I define a system as function and structure, we need to superimpose this function on top of the structure of structures, run it to detect the emergent functions. This is where maturity enters into play with the metrics of maturity. And we are developing, if you're interested, we have papers on that, and I wrote a book as well. And then emergent structure, the structure that you forgot, then emerged from the human-in-the-loop simulation by observing the activity and therefore deducing by activity analysis the emerging functions. So we have criteria for doing this, like shared situation awareness, speed and precision, resilience, trust and collaboration. We are doing this on this the FCAS system, the Future Air Combat System at the moment. You need to I'm going to go fast now because I want to reach the end, but another point that we have to take into account when you do this scenario-based design is the separability of systems. There are systems that you can separate and study in isolation, and other you need to study the whole thing. We have at the moment 3 kinds of interaction models, systemic interaction models: supervision, mediation, cooperation, and they are embedded into each other. So in fact, when you develop this PRODEC approach, then you can figure out if it's a mediation, a cooperation, and if you are not sure, then you run a simulation, etc. So I pass on this one. This is the Mohican project. I pass on this. I already showed this simulation. We have in Mohican. Mohican was a project where we tested, virtual assistant in combat aircraft that included a lot of knowledge about the many other agents interacting among each other. All this was coupled with a data analysis system. So when I talk about human-in-the-loop simulation, I'm talking about these kind of things. Then you have this BPMN diagram coming out, and then here after that, by hand, you have to figure out, what is emergent compared to we compare the task, the activity, and the as-is and the to-be. I mean, there are four things that to be compared, and then we try to find out the emerging functions. Sorry, it's in French here. Fonction emergent, emerging functions, and then all this is re-injected incrementally into the system itself. So in fact, we start with the task analysis. We develop a prototype, do a human-in-the-loop simulation, observation of the activity, do a structure function analysis. Then we can iterate on the metrics. And then you have a tangibilization here where you do this kind of thing could be called an ontology of the system here. So this is the thing. So in fact, here are the buzzwords. The human factors enter into this, PRODEC, and the formative evaluation and agile development and human-centered design. So in fact, what we come up with is what we call a systemic ontology of the system that we follow. And don't forget the maturity issues along the way. Thank you very much.
Thank you very much, Guy. As always, a super interesting webinar with you. We open the Q&A, so we have already a question. I have some that I already raised for myself during your presentation, but I'm encouraging the participant. We have 10-15 minutes still with Guy to have him answering some questions. I just want to remind that it's the 4th webinar with Guy. Actually, we started last year in October and November with the first two webinars, like a series, if you want. The first one was about the role of the people in the interconnected systems, and we follow with the problem-solving procedures, how people are handling unexpected situation. And we came back early this year with the use cases of human system interactions from different industries. So we had 3-4 projects on which Guy was involved, and now this final one is on scenario-based design. So one of the question actually, Guy, that came into the Q&A is, do you have some reflection to share about the tools used to model scenario? Why you have used BPM, BMP, and not CSML or Capella or other more MBSE tools?
We have used CSML, but CSML is now that I describe what the structure and function are about for systems, CSML is about structure most of the time. It's very difficult to include events and humans there. So in fact, BPMN is more a process by definition. BPMN means business process model. BPMN was developed in the management more than anything else. So, but so we found that very useful, but we are not very happy with BPMN as well. So in fact, this is the reason why we are developing PRODEC, that is an alternative to both CSML and BPMN.
Right. And we know any modeling, it's a replica valid of the reality, and no model is perfect. There are other models which are better than some models better than the others. Now, one of the reflection was in the chat, not in the Q&A, was that one of the participants really liked the idea of considering the humans as a system. I think we all maybe try to think in social human, social technological system. I would not like to think we're just technology and human system, but you may have a combination of them, or even, more abstract, like the transportation system, or academic system and so on. Can you comment a bit on that?
Well, that started because we had for the last 3 years we have a working group called Human Systems Integration Working Group within INCOSI, the International Council on System Engineering. And for the last 3 years, we had meetings every 2 months because we wanted to write the next version of the System Engineering Handbook part, the HSI part. And then we ended up with conversations on what a system is about. So 24 countries. This is not coming from my head only. So we had a lot of discussion, and we came up with the result that when we talked about system, we talk about representation. It's a reduction, if you like, of the real world. So it could be an artificial world, machine system, if you like, or a natural world, human. And when you, as I said before, when a physician, a medical doctor talks about the cardiovascular system, it's not a machine, but he wants to represent the cardiovascular system in a way that you understand that it works. That's the thing. And sometimes they represent the cardiovascular system with equations, flow dynamic system, the fluid dynamics, these kind of things. So in fact, we say, well, and that's where the first remark. The second remark is, among us, there were people involved in artificial intelligence, AI. In AI, we are talking about agents. There is a very remarkable book by Marvin Minsky in 1985 called The Society of Mind. If you didn't read it, I really advise you to read this book, The Society of Mind, M-I-N-D. And where he talks about what is an agent. And he said an agent is a society of agents. So in fact, it's exactly the same as in system engineering. A system is a system of systems. And then can we say that the human is an agent? I don't know, but it's a representation. This is the same thing. So in fact, system and agents are the same thing, except that one is coming from system engineering and the other one, or system science, it's better, and the other one is coming from AI. And this is something that we are working on right now. We have a group working, on this kind of thing, on knowledge representation. In the United States, they've called that AI for SE, SE for AI, AI, artificial intelligence for system engineering, and they call it, AI, the number 4, SE, etc. So it's interesting because here there is a very interesting conversation to have how to model human systems integration. If you want, for instance, with SysML is extremely difficult because SysML didn't capture very, very well these kind of things.
On the same, before I throw my questions in, so there are some coming. It's from the same person that asked about the modeling system. Ricardo Reyes said, an organization is a system. Do you see a specific tailoring need for organization readiness level than using system readiness level that already exist in some organization?
I would say that I cannot answer to all questions accurately, of course, but here my take, if I take this question properly, I would say that the dynamics of organizations and the dynamic of people and the dynamics of I don't know, an aircraft or an air traffic control center are different. So in fact, I think that is one attribute, the dynamics that would make difference in the setup of organizational readiness levels. And probably in the beginning, we're gonna be very case-based, so this is the answer I can give to that. I mean, I would not advise to use TRLs for ORLs. You have to redesign the ORLs.
Thank you. There are one or two more questions, but before I throw into that, one of my, I would say, worries in this, and also you have given a lot of hints how to make that comprehensive. When you do scenario-based simulations or design, how do you make sure you are exhaustive and you have not leaving us outside use cases that will be important for your design of that system?
Well, I had this question many times already, so 100% satisfaction is impossible. I don't know the percentage there, but if you don't do it, it's very dangerous. I think it's important to test the system. Are the flight tests, I've been working in flight tests with Airbus for several years. How do we develop the flight test? Are we sure that we cover everything? We try. We landed on the North Pole, we landed in the Sahara, we landed in, we tested in many, many situations. And we have scenarios that you cannot believe. So my answer to your question is not a question of number of scenarios. It's a question of the number of experts that will judge that the scenarios are enough.
Yeah, I totally agree with that. And I was thinking that also you may have a link also with the maturity levels of all the readiness levels. Because if you think with the diversity of experts that are with you, and then the maturity of these scenarios, then you will account not for all, because 100% doesn't exist, but at least for the most important ones. Right. So one of the question is, in a complicated environment where drones and manned aviation are using the same airspace, how we can use HSI to understand this complex ATM system in order to integrate drone operators without aviation knowledge with manned aviation? I mean, it comes back to what you just said. It's about the knowledge. I mean, you can't design a system without the knowledge.
No. and knowledge and expertise. I mean, it's and so it's a long answer. I could start, but this is the problem with this kind of thing is you know, you have to start. We have started. We work with my students, my master students, this year on this remote carrier. You know, the remote carrier, the drones that are flying together with an aircraft, a combat aircraft. And in fact, we took 2 of them plus an aircraft. So of course it's not 100, but you have to start somewhere. And you start to understand some simple ideas that need to be injected in the system. And then you can increase the number of drones, for instance, or number of, you know. So now if you think about, and I didn't work on this yet, probably one day I could, but I don't know when. If you have lots of drones, you know, in the civilian world, then as I said before, the more you have autonomy, the more you need coordination rules. This is a law for me. So in fact, we need to design the airspace in a way that that the coordination is well done. This is the top model, you know, the technology organization people. So in fact, on the regulation side, there is a lot of things to find out. And in fact, in order to find out this, expertise is key, but more than ever, human-in-the-loop simulation is key. You need to simulate things where it's not dangerous in software stuff, you know. but I think this is important. You need to find out the emergent properties of this system. Emergence, you know, a complex systems, any complex system has emergent behavior, emergent properties, and you need to discover what they are. And this is where you increase the maturity, in fact. The more you have you know about emerging or emergent properties of a system, complex system, the more maturity you have.
Right, the last question that we have, and we're approaching our time, is, and I think it's an easy answer to that, because as I mentioned in your third webinar, you presented several use cases of HSI from different industries. So one of the participants is asking if he can have some less complicated or some easy and practical example in applying this, what you presented. So do you have other examples than those that you mentioned it before, with even the one that you presented today with the military air traffic control system?
Yeah,
yeah, go ahead.
I could, you know, I have a very simple example in the, you know, we have worked with Total Energy, but unfortunately I cannot talk about everything. Sorry. I know that they are not competitors there to Total, but so they are very, very interesting thing that we found out when we've been working for the last 4 years with Total Energy on the the development of fleet of robots on drilling platform on the ocean. And in fact, they want to replace the people by. I talked about that in the last seminar a little bit, and so in fact, there are things that we didn't discover until we tangibilize enough the thing. So in fact, we have a platform in Lac in the Pyrenees, in the south of France, a physical platform where we can use robots and installations and things, and then we replace the virtual stuff by a more tangible stuff, you know, and more real robots. And then of course you have to mix this the virtual with the tangible, you know. It's really this kind of thing. So I don't know, I cannot go into more details, but it's here you have a problem, and we are doing this for a long time in the Air Force. You know, they are playing when they train the personnel in air combat. They have virtual world in parallel with the real world. You know, it's I don't know if you saw the movie with Tom Cruise. I mean, forgot the title. Anyway, so it's this is what they do, and so we can mix this kind of thing, and you discover the emerging properties. You know, this is interesting.
Right, yeah, I promise that was the last, but it came a very last minute question, which is interesting, and seeing that we still have a number of attendees, I will throw it to it, maybe 2-3 minutes on it. It's coming from Max Schenk. Max, it's a pilot and the president of the German Pilot Association. It's a great presentation. 2 quick questions. How do you distinguish autonomy from automation? And depending on this definition, how can autonomy be simulated? I guess goes back to your slide where you show that the system could be supervised, mediated, autonomous, and so on.
Yeah. So one part is this. So the level of the interaction model. You know, we are okay.
So how do you distinguish between autonomy from automation? And how you can simulate autonomy if possible?
Yeah, automation is the implementation of procedure in a machine. But you can automate people with operation procedures as well. I mean, if you apply the procedure by the letter, then you're an automaton. You're a robot, if you like. Okay, and if you put it in the machine, then you have a robot. You know, this is automation. Autonomy is when the system, whether it's a human or a machine, is capable of solve a problem that is not necessarily in the form of a procedure. So in other words, it's very context dependent, and it's based also on a lot of maturity. It's related to maturity. Autonomy is related to maturity. You know, maturity for human beings, legally speaking, is 18 years old. During my time was 21, but now it's 18. I see some people 35, questionable. So maybe myself also have a problem with maturity on some aspects of life. You know, but because you cannot handle systems, and especially in unexpected situations. So that's, but it's not the definition, by the way. I would say autonomy is when you can, you know, you cannot be fully autonomous. You know, the autonomy deal also with collaboration and trust as well. We started to discover that. So in fact, when you have an autonomous system that does something by itself, then you have to trust him, because otherwise, if you don't trust it, you stop it. You know, this, so it's there are lots of things to define when you define an autonomous system. First, this issue of trust and autonomy. The second is the issue of context sensitive and understanding the context in order to find solutions. The third one is to live with the others. This is the coordination. So if you don't have, for instance, when you drive on the road, you are autonomous. But if you don't have road rules, it's a mess. So you need to define coordination rules with autonomous systems. So that's the thing. But this is not all. I think there is a big space for discussion there. I mean, it's really, yeah. But automation is clear, procedures.
But then I think to finish, because I know now there are popping more questions. The more you answer, I think it's more appetite. Can we simulate autonomy? That was the second part of that question.
Well, of course, if you develop a system that could, a drone, for instance, but is a drone a fully autonomous system? I'm not sure. Do we want that? I don't know. Yes, you can. We have made drones that can fly, and you know, they can take into account the wind. They can take into account I don't know if they are able to take into account the wind shear exactly, but we have done things, but the problem is the world. Is it in a closed world or in an open world?
Yeah, the context is very important. I think you dwell on that in the beginning of your presentation, how to recreate the context for which you designed. So.
And something I don't want to darken the presentation, but I'm working on context for 40 years, and I'm not sure I can define the context properly.
That will be for a different webinar. There are 3-4 more questions coming in, but I will stop here because I see the audience is dropping. So thank you very much, Guy. And I want to disclose that together with Jörg and Eurocontrol team, we are looking at on a way to engage Guy on a more direct and face-to-face events, because I think it's great that the appetite that you are opening for in this webinar, and see how we will continue. So thank you very much, Guy. Great webinar as always. Before closing, I want to announce that Dana has just published an update to the webinars. Because Hans Christian Jeter, the professor that we had to start a couple of months ago, he had a personal event. So we pushed the second part with him for the augmented reality and virtual reality on the 25th of September. And the third one that was supposed to be in September, then will be December. And in July, we have another webinar with Steven Schorer. On behalf of Eurocontrol team, Clar, Dana, Jörg, and myself, and of course, on Guy, thank you very much, and see you at the future webinars. Guy, thank you very much.
Thank you for having me. Bye.